RAM stands for Random Access Memory. It is the computer's short-term workspace, holding only the data needed for immediate, active tasks. Think of the hard drive as a library, and RAM as your physical desk. When you need to work on a file, it is pulled from the drive into your RAM for the CPU to process instantly. This quick access allows the CPU to perform operations without waiting for slower storage devices, keeping your system responsive. RAM acts like your desk. It holds the work you are actively doing right now for instant high-speed access. Storage is your filing cabinet. It keeps your files and programs safe long-term, even when the power is off, though it takes longer to retrieve them. The CPU is the brain of the computer, but it relies on RAM for fast data access. The communication is managed by the memory controller, which acts as a sophisticated gatekeeper. When the CPU needs data, it sends a request signal through the memory controller. The controller validates the address to ensure the request is safe and accurate. The controller then passes the request to the specific memory address in the RAM. The memory cells are energized and the data is retrieved. Once retrieved, the data travels back through the controller, which prepares it for the CPU to process at incredible speeds. By managing these requests, the memory controller ensures that the CPU always has the right data at the right time, minimizing bottlenecks and maximizing system performance. A memory cell is the fundamental building block of RAM. It consists of two primary components, a capacitor and a transistor. The capacitor functions like a tiny bucket that holds an electrical charge. This charge represents the bit of data. A charged capacitor indicates a 1, while an uncharged one indicates a 0. The transistor acts as a precision switch. It regulates the flow of current, determining when the capacitor can be read from or written to by the processor. At the most fundamental level, computer memory works using binary logic. Each individual cell within a RAM stick stores a single unit of data, known as a bit. A bit can only exist in one of two states, 0 or 1. In our hardware, this is represented by the electrical charge of a tiny capacitor. When the capacitor is uncharged, it represents a binary 0. When we write data to this cell, we fill the capacitor with electricity. A charged capacitor represents a binary 1. By orchestrating millions of these cells simultaneously, your computer can store vast amounts of complex data using nothing more than simple presence or absence of electrical charge. To manage billions of data bits efficiently, RAM organizes memory cells into a two-dimensional grid, similar to a spreadsheet. Each cell is uniquely identified by its specific row and column coordinates. When the CPU requests data, the controller sends an address that specifies a row and a column. The intersection of these two lines pinpoints exactly one memory cell. This grid-based architecture allows for extremely fast access times. By selecting a row and column simultaneously, the memory controller can read or write data almost instantaneously. While this grid is tiny, real-world RAM contains millions of such matrices stacked together, creating a massive, organized highway of information for the processor. Every single piece of data in RAM resides at a specific coordinate, known as a memory address. The CPU acts as a master controller, requesting data by sending these unique addresses. When the CPU needs information, it places a specific address onto the address bus. This signal tells the RAM precisely which cell to activate. The RAM locates the requested data at that exact coordinate and sends the stored bits back to the CPU via the data bus. This constant cycle of sending addresses and receiving data is how the processor interacts with your system's memory at lightning speeds. DRAM stores data in tiny capacitors. These act like miniature batteries, but they are not perfect. They naturally leak charge over time, meaning the data they hold will disappear if left unattended. To keep the data intact, the system performs a refresh cycle. Every few milliseconds, the controller reads the charge level of every cell and immediately writes it back to full capacity. The CPU and RAM operate in perfect synchronization. The system clock serves as the heartbeat of the computer, dictating the timing of every single data operation. Frequency is measured in megahertz. 1 megahertz represents 1 million clock cycles per second. Higher frequencies mean the memory can handle more operations in the same amount of time. RAM must be fast enough to keep up with the CPU. When the clock pulses, the RAM performs a read or write. If the clock speed is high, these pulses happen in rapid succession, resulting in faster system performance. In summary, higher megahertz means more cycles per second, allowing the RAM to keep pace with modern, high-speed processors. Latency, or CAS latency, represents the delay between the CPU requesting data and the RAM delivering it. It is measured in clock cycles. While bandwidth tells you how much data can flow, latency dictates how quickly that flow starts. Generally, lower latency timings result in a more responsive system. A DIMM, or dual inline memory module, is the standard physical format for computer RAM. It acts as a bridge between the memory chips and the computer's motherboard. The rectangular modules mounted on the board are the actual dynamic RAM chips, where your data is stored electronically while the power is on. At the bottom, you can see the gold-plated contact pins. These pins create a precise electrical connection when inserted into the motherboard's memory slots, allowing the CPU to read and write data with high speed. By using a standardized design, DIMMs ensure that memory modules are easy to install, replace, or upgrade, making them essential components for system performance. Standard memory technology transfers data once per clock cycle on just one signal edge. This is known as single data rate memory. DDR, or double data rate technology, revolutionizes this by transferring data on both the rising and falling edges of the clock signal. By capturing data twice per cycle, DDR effectively doubles the bandwidth without needing to increase the clock speed of the memory itself. The evolution of double data rate memory has been defined by a constant pursuit of speed and power efficiency. Starting with DDR3, we established the foundation for modern high-speed memory architectures. DDR4 introduced higher density and significant improvements in power consumption, becoming the standard for years. DDR5 represents the latest leap, doubling bandwidth and enabling much faster data rates while maintaining superior efficiency. Crucially, each generation requires a different physical slot on the motherboard, preventing accidental installation of incompatible memory. The capacity of your RAM is critical for system performance. Think of RAM as your high-speed workspace. When tasks pile up, your computer needs enough space to hold all active data. This is what we call system memory. If your capacity is too low, the system is forced to move that data into virtual memory, essentially using your slow hard drive as a temporary overflow area. This constant swapping is significantly slower than RAM access, which causes the system to stutter. Increasing your capacity prevents this, keeping your workflow in high-speed memory. When a computer runs out of RAM, it doesn't just stop working. Instead, it uses a technique called virtual memory or swapping. As you open more applications, RAM fills up. Eventually, the operating system needs a place to store data that isn't currently being accessed. The OS offloads this data to the hard drive, creating what we call a swap file. This keeps the system stable, but accessing data from the drive is much slower than from RAM. Because the hard drive is significantly slower than RAM, you may notice the system stuttering. This is the physical cost of exceeding your available memory capacity. Multitasking relies on the ability of RAM to hold multiple applications simultaneously. Instead of reloading from slow storage, your active data waits in these memory buffers. When you switch between apps, the CPU accesses the data instantly from these sectors. There's no need for time-consuming reads from your hard drive or SSD. If an app is not in RAM, the system must fetch it from storage, causing a noticeable delay. More RAM means more applications can stay ready for immediate switching. Essentially, RAM acts as a high-speed workspace. The more space you have, the more you can do at once without the performance hit of reloading. In modern gaming, RAM acts as the bridge between slow storage and your high-performance CPU. When a game runs, it needs to constantly fetch textures, geometry, and physics data. Without enough RAM or fast bandwidth, assets cannot load into the processor in time, causing stuttering or objects appearing out of nowhere, known as texture pop-in. Watch as game assets stream from the slow storage into the high-speed RAM grid. Faster bandwidth allows these cells to fill up instantly, keeping your frame rate smooth and consistent. Higher capacity means more game world detail is held in memory, while higher speed ensures that your system can swap these assets with minimal latency. For basic usage, 8 GB is recommended. This is sufficient for web browsing, office docs, streaming. For prod gaming usage, 16 GB is recommended. This is sufficient for modern gaming, heavy multitasking. For creative usage, 32 GB plus is recommended. This is sufficient for 4K video editing, 3D rendering. Troubleshooting RAM issues often starts by identifying key warning signs. Faulty memory frequently leads to unpredictable system crashes and the dreaded blue screen of death, often triggered during memory-intensive tasks. If your system shows signs of memory failure, the most effective first step is to physically reseat the RAM sticks. Poor contact between the pins and the motherboard socket is a common cause of hardware instability. Carefully remove the modules and reinsert them into the slots, applying even pressure until you hear the locking clips click into place. To summarize, random access memory is the high-speed, volatile workspace of your computer. It operates as a massive grid of individual memory cells, storing binary data that the CPU needs immediately. Because it is volatile, it requires constant power, providing a clean, temporary stage for your active tasks. Without this efficient cell-based feeding ground, the processor would be constantly waiting for data from slower storage, significantly hindering performance.